Thank you, everybody. Thank you for coming here today. Hopefully this is going to go well. I don't have voice, so probably in the middle of the seminar, my voice is going to end. My computer crashed 3 times yesterday. And I have learning in my title. So we'll see how this goes. Everybody's doing learning. My presentation is going to focus on the learning aspects of control. And a few miles from here, people are using learning for self-driving cars, for manipulation, for walking, and for pick-and-place problems. Okay, it goes also under the word of AI, artificial intelligence. I'm actually one of the faculty that believe that we have oversold this term, and faculty actually haven't done too much for stopping this nonsense. And if you just look at the investment on self-driving cars alone, we have 80 million. These are old numbers. Probably are around 120. The whole Apollo mission costed, I did the math, roughly $150 billion in today's money. Okay, so we're very close. There's not self-driving car out there. But what I'm going to do is just way too easy. I've been in a lot of presentations to criticize the hype. So I'm not going to be negative. It's very easy to show things that fail. So actually, I will try to be positive and tell you a little bit my view of learning and where it can be beneficial. Okay? So I'll divide, talk is divided into 4 parts. What I think 3 key ingredients for autonomy: constraints, predictions, and learning. My classification is learning of this overused word. Then I'll tell you, this is the technical part. Is going to be this technique that I call iterative learning, predictive control. And then some thoughts of what is new, what is old, the real benefits of learning. Okay? Stop me anytime. On our website, there's a video and slides and papers. You can see a 30-minute version of this talk on the recent conference, Learning for Dynamics and Control at MIT, together with many other really interesting talks from people doing learning and control. In Berkeley next year, deadline is in December. Okay, so come there. It's going to be the second conference on L4DC. Okay. You'll see a lot of nice videos, Marco said, thanks to funding, CTO of Hyundai Motor, CEO and CTO of Alex Howe and Dan Sugar from Nexttracker, and many other companies. The work of learning MPC was started 5 years ago by Ugo Rosulia. Great thanks goes to him on putting this together. When we teach controls to undergraduate students, we use the inverted panel, right? How many of you have taken reading equation inverted panel? Everybody. This is taught to explain to you what is nonlinear dynamics abstraction, how you do linearization, what is an equilibrium point, what is stability, Lyapunov stability, and how you do a stabilizing control design. What is the problem is that once you learn this, you really won't be able to do not even the simplest control design in any of these systems, okay? And why? Because all these systems have constraints in the design. Okay, so what I've been trying to think is how we think a lot about undergraduate education. How do we change this problem so we can actually teach constraints? And so now I'll take the inverted pendulum and replace the stick with a wire. And so this becomes a ball in a cup problem. I want to swing. I'm moving the cup. I want to swing the cup so that the ball goes into the cup. As simple as this. You can write the modeling with 8 states: x and y, position and velocity for the cup, x and y for the ball. There are constraints on the acceleration of the cup, right? Because you can't go super fast and catch it immediately. There are constraints on the relative state. The distance between the ball and the cup has to be less than L, okay? And your goal is described as a constraint. At the end, at some time t, the ball has to be in a cup. Very simple. All what we teach doesn't really apply here, right? Just want to bring the ball in the cup. Don't care about Lyapunov stability, linearization, equilibrium, and so on. Okay? So constraints dominate the design for this problem. And the simplest way to do this, the most disciplined way, is to write it down as a infinite horizon optimal control problem, where infinite here is a very long horizon. It's the t where the cup will go, the ball will go in the cup. So here you have some costs. You have the model of the ball in the cup. You are looking for a set of feedback policy. You have constraints that I've just described before. And at some time t, the ball has to be, it's your target set. The ball has to be in the cup. We all know, you take classes on this topic, that this is a hard problem, even if your model is perfect, even if your constraints are static, okay? And in MPC, that's what I've been doing for most of my career. What we do, we actually take this long horizon or infinite horizon problem, and we solve it as a short, very short finite horizon problem. Right? That's all what it is in MPC. It's exactly the same problem, cost, constraints, and model. The long horizon is replaced now with N. Okay? Looking for a set of feedback policy that minimizes costs and these constraints. MPC applies the first input and keeps repeating the optimization the next time step. So it's nothing but the first feedback policy, pi 0, implemented with actual current state. So what it is, you take the first policy and implement the first state. It's a big community. There are conferences, there are MPC conferences from both robotics and as well as it started actually in the chemical world, okay, chemical engineering world. There's a lot of theory, there's computation, there's practice. The classical theory actually tells you, this is the first example that I do in my MPC class, that if you do not design the cost to go and the terminal set properly, nothing is going to work, even for linear, perfect models. Why? Because you're short-sighted. So in the ball in the cup, you're very short-sighted. You have to swing in the ball, and you basically want to make sure that it lands in a set where you can catch it. Okay? So this set has special properties called the control invariant set. That's not enough. You need a cost on this set, which is a control opponent function that actually guides you towards the catch. Okay? And so these two objects are well studied. There's hundreds of papers and books on control opponent function invariant set. The theory goes like this. An invariant set is basically an extension of an equilibrium point. It's a set of states for which there exists an input at the next step you are in this set of states. Okay? It's, again, an extension of an equilibrium point. How do you compute this? Here is a simple example. Linear discrete time model. Your goal is to bring the state to 0, and you have input constraints. You're going to write down my set controllable in one step to S, the pre of S, is a set of points for which there exists an input such that AX plus BU is equal to 0. So the next state you go in 0, and you satisfy input constraints. So this object, the set of X such that exists in U, remember, you probably studied somewhere in linear algebra. When you have an exist operator, this is a projection, right? So to compute this object, you need to project, and projections are hard. And now you have the one-step controllable set. An invariant set is a fixed point iteration of this procedure. Okay? So yes, you can use MPT Toolbox for linear systems. I contributed to some of these algorithms when I was a PhD student. Or for instance, you can solve for nonlinear systems, trying to find the level set of Hamilton-Jacobi-Bellman equation. Okay, and this is a student of Claire Tom, who was a professor here. I'm going to refer to invariant set as safe set. French call it a viable sets. Okay, control invariant, safe set of viable set, they're all the same thing. Control upon a function. It's a function such that it's positive definite that decreases along the closed loop less than the stage cost. Okay? How you design this function, again, is very hard in general. If you take the simplest linear model, you take a quadratic function, what you can do, and you have constraints. You can solve the LQR for the unconstrained problem. Then you can compute an invariant for the closed loop system when this is the LQR. Okay? And now, subject to state constraints and input constraints, this you do it the way I showed you before. And now you can say that the LQR optimal cost is a control opponent function in the terminal set. And you can do piecewise quadratic opponent function, LMI, sum of squares approaches. Okay? So there's a lot of literature, very hard. If you ever played with these tools, finding control opponent function in 10 states with constraints is basically impossible at this point. Okay, so what does the computation tell you? Well, in MPC, I need to compute this policy. There are two ways. The first one I call offline-based. You do a lot of calculations offline, and then in real time, you just apply the policy. So you compute the policy, you evaluate the policy at the state. That's just a lookup table. One way to compute this policy is dynamic programming, for instance, right? Value iteration. And we all know that you need some form of gridding. More than 5 states, things don't work well, so you need some model aggregation and reduction. Okay? By the way, everything in approximate dynamic programming in first learning is about computing this policy. This is what AI is, right? This is function approximation. Okay? The other way is actually online. simple, what I mean online-based. Offline, you just set up an optimization problem. And then online, you do a complex algorithm, okay? So for instance, you could use an interior point method or a sequential quadratic program. This doesn't give you a policy, it gives you the policy at the given state. Okay, that's the online approach. Very hard to run this in real time on embedded solvers. However, if you convexify, then there are fast convex solvers. And this is really what I've been focusing on the past 10 years, how to balance this online versus offline approach. There are excellent online-based solvers. You can make your startup based on IP-opt, and it's just excellent, convex and non-convex, or CVX. There are offline, you know, that there is, you know, what is called the explicit solution for linear systems. That's what was my PhD work, where you can pre-compute some of this table without gridding. However, this works only if your constraints. Again, constraints is low, not state. Like it works, explicit solution works in 100 dimensions if you have 3 constraints. People working on mixing, pre-computation and online optimization, MPC on FPGA. We did some work with Sergey Wiki 3 years ago, where actually we were moving away from digital computing and running MPC in microsecond. Actually, we have a nanosecond implementation. We're just using an analog computer. If you don't know of any of these tools, MPT, YALMI, Pacado, CVX, GAMS, IP-opt, every tool, but there is an issue. Okay, there's an issue. Go back and pick one of these and learn one. Okay, good. And you know, just not to advertise my word, you know that the Falcon 9 is controlled by CVX. The landing is controlled by CVX. Okay, so recently we had Lars Blackmore presenting. It was very interesting talking to him and how he designs the fins. And is using real-time optimization to land the rocket. Okay, what do you do in practice? This is our self-driving car, like as same as any of the cars that you see out there as a test. And somewhere, all the many companies in the Bay Area doing these things, they have MPC at some point, either in the Bay Area planning, meaning do I overtake or not, either into motion planning or in the path following, okay? They do because you need to replan, okay? Things move around, you're uncertain, you need to optimize and replan. And so what happens if you use a formal approach, the one I showed before? It happens that there's no invariant set and terminal costs. You play with the horizon, okay? And actually, there are companies that give you data where human drive, with drones, where human drives drive, and you can use this data to actually compute your cost, okay, the cost to go. So you basically a data-driven cost to go. It's what a lot of companies are using out there. Don't minimize over policy. This is very hard. Most of the time, you minimize over an open loop sequence, okay? To write a theorem, you need time-invariant constraints most of the time. Theorems with time-varying stuff it's hard, okay? Then you need to bound the way this changes with time. But everything out there is time-varying. You have your constraints depend, your area where you can drive depends on the agents, okay, where they're going to go. Their forecasts are uncertain and will change with time. So most of the time what you do, you basically replace the deterministic constraint with sample-based scenarios, okay? These are all the 5 top things that I believe is gonna happen for my pedestrian. You cannot use a genetic solver. You need to exploit the structure of this optimization problem. You need to smart initialize it. And in my talk, I'm going to write, you initialize the state with the major state. We know that localizing yourself is probably one of the hardest problems, right? And this is where you want, there's a lot of work going on. And this is one of our tests, not too different from what you see out there. This is running real-time optimization, running IP-opt in real time. And again, if you see a pedestrian, this pedestrian was forecasted its motion. The motion will change the constraint, which will change the solution. So let me go to, I hope I convinced you that constraints and predictions are important, okay? There's no way you can do any autonomous system, challenge them without forecast. Let's move to learning, okay? As I say, it's an overused word, so I'll try to give you my definition of learning. And the idea is that, again, when we teach this inverted pendulum, we don't use the fact that in many of these examples, some of these tasks are iterative. There's a piece, at least a piece of it that is repeated, okay? This is my ball in a cup. This is Luca. You give him he doesn't know what to do at the beginning, okay? And this is a kename, it's a Japanese toy. And he keeps trying, and he has tried a week before doing this video. But at the end, he succeeded and is very happy. Okay? So here's I've been thinking a lot about learning, looking at literature. So here's my classification of learning. It's 3 aspects. Okay? First one is you didn't know how to do a task, and you learn to do this task, but just keep trying, like kicking a ball mid-air. Okay? I call this skill acquisition. Okay? The second one, when you keep kicking balls mid-air, then you get really good at it. Okay? Then you become excellent. This is what I call the guy. This is Bales. He knows how to kick balls mid-air, but then he keeps doing it, and performance improvement is what brings him at the top level. And then if you keep kicking ball for all your life, you just go in open loop. Okay? And why you're doing this? Your computational load goes down, so you can do other things, right? If you think about it, it's very interesting. I've been looking at this video with faculty. It doesn't close the loop even on the touch. It's trying to close the loop on his vision system, okay? You see, it's not touching it, okay? Good. So if you go to the neuroscience department, they say, oh, this is too simple. I agree, okay? This is not a standard definition of learning, the acquiring a skill, improving performance and load. And this happens, it's quite complex the way this happens. We acquire a skill, we get better at it, and then as we get better, some is stored somewhere in our body, and we do other things. It is a major oversimplification, but I claim that it is enough for robotics. Okay? As a matter of fact, in the robotics field, you have the learning from expert demonstration. Stanford is one of a key player in this, transfer learning, where you do not know how to do something, okay? And then you keep trying, and then you succeed. Performance improvement, this is probably by far the most studied. Most of the reinforcement learning paper, they will write sentences like this: suboptimal successful trajectory from a demonstrator available. This means you know how to do it in the first place. It means that you're giving you an environment. A control community will assume a control environment set is available, without telling you how to compute it, okay? And then all the load reduction is all these people doing lookup generation, neural network on chips, trying to, once you have a policy, how to make it fast computation. So I'm going to, how does it look? These 3 forms looks for robots. I'm going to use my 1 to 10 scale vehicle. I teach a class on vehicle dynamics. We use this for our undergraduate students. This is skill acquisition. You try to park, and it's a very complicated maneuver, right? There are the dynamics, there are constraints, there's the friction, which is not well modeled between the tire. And after 11 iterations, you keep trying, and you do drift parking. Okay, skill acquisition. Performance improvement, you ask this car, learn how to race faster and faster. Solve this problem minimum time. So you go center lane, very slow, okay? And as you acquire data, you improve your model, you improve your cost, and you get better and better, okay? And at some point, this will go as fast as it can. I should try to increase the video here. Is there a way to increase the audio? It's okay. It's fun to hear the wheel scratching. Okay. Computational load reduction. Once you have learned the minimum time solution, but you see this is the lap time as the lap goes down, okay? Now you can stop predicting. You can use your data around your state to actually look up the solution. You see the computational load goes down, 10x, is not predicting anymore, and the cost is the same. You're doing same lap time with 10x of your computational load on the CPU, okay? So this is the third part of my talk, how we do this. I'll show you more of the math behind it. It's very simple. It's a super simple idea. You can code it up in today when we go tonight, no, this weekend. Yeah, on Sunday, okay? Iterative learning, predictive control. Here's the idea. Assume this task is an iterative. You start always from the same state, and you end always this final state. And my notation will tell you that I'll use this double index. This is time. This is the iteration number. Okay? This is the state of the system, time t at iteration 0. I'll explain these things for the iterative, the performance improvement case. So I'm assuming somebody has given you the 0 feasible one. Okay? So And then I'll tell you more about how you compute the first one. This is the state at iteration 1 at time t. Okay, so because you have changed your policy, then the trajectory will look different. Okay, in practice, okay, what happens is that if you fix a control policy, this is my MPC policy, at iteration 0, I'll fix it, and I keep trying, I really will have a cloud of points, right? Because there is noise, and that's why you have, and there is a lot of uncertainty. And so these, in general, in the reinforcement learning communities are called rollouts. So the iteration, you fix a policy, and then you have 100 rollouts per iteration. Okay? So this is a plot where you see 2 iterations, 2 policies, and 100 rollouts per iteration. What I'm going to show you is all deterministic. You can go on our website. You can see the stochastic version, the robust version. The students have to write paper, and the basic idea is always, it's very simple, and it's always the same for the same and of the deterministic case. So you're not going to see cloud of points. You're going to explain you the idea in the deterministic perfect model case. Okay, remember the biggest issue with MPC? How do we get this terminal causal terminal constraint? Well, can I use data to update my cost function, cost to go, and my safe set, and possibly my model? Let's assume my model is perfect. I'll give you a few hints on what happens when the model is different. Here is the idea. Let's focus on safe set. Assume somebody gave you a trajectory that brought you from XS to XF, state input pairs. Okay? What can you say about this state input, this set of points? It's a control invariant set. If you got under perfect model, if I'm here, there's an input sequence that will bring me to the terminal set. It's a discrete control invariant set, right? Okay? So what do you do? Well, use this as a terminal condition of your MPC at the next iteration. So iteration 1, you start again from here. You are short-sighted, look ahead, but you have to land in either here, or here, or here, or here, or here. Okay? And so I'm looking 2 steps ahead. I decide to land in here. That's the best trajectory. This point here, okay, is where I'm going to land as I apply the input that I predicted if there is no model mismatch. I repeat the optimization again, and again, look at this. This is what you know that happens if you ever implement MPC. The trajectory will look different because your horizon now is shifted. This is the best thing to do now, to land in X04, and so on, right? So at the end, because you're landing into an invariant set, this is what MPC proves, that you will succeed. You'll end up in XF, even if you're short-sighted. Because in the worst case, if you can't find a solution, you repeat exactly the one you've done before. Okay? But you're on the same page. But there's something that if you are optimization savvy, something didn't sound right when I was describing this. Yeah?
You piece together multiple optimal subpaths. The resulting path is not necessarily optimal.
Yes, we have to prove that. Very good. And then we also have something from a computation point of view. When I said or are not good. Every time optimization guys say or, something has to, ors are bad, okay? Mixed integer optimizations, NP-hard problems, right? Okay, but so at the end, assume that you have these data points, the union of the sample safe set before and now my trajectory is another safe set. And in general, the safe set at iteration j is all the data points where you converged at iteration, where you got to the goal, okay? Here's how you get rid of the or. For linear constraint systems, if you take the convex hull of these points, then this is actually, you can prove very simple. This is linear algebra, that this is a control invariant set. So you don't have to solve a mixed integer problem. You can actually land in the convex hull of the stored data. And in this way, you also get rid of a lot of data, okay? So what about the cost? I told you about the terminal set. What about the cost to go? Simple idea as well. You have an iteration. You start from x0. Somebody showed you how to go. Now this time, the state is in 1 dimension because I want to plot also the cost to go. Somebody gave you a demonstration to go out to go to XF. I have 4 points. I have the actual measured data, so I compute the actual cost at these points. HX03, the realized state with the realized input, the realized state with the realized input plus whatever was this, and so on, okay? Take the epigraph of this points. So take the epoch of the convex hull of this point. It's called a barycentric approximation. My claim, you can prove it, that this is a control Lyapunov function. How do you write this? It's very simple. You're looking for a set of multipliers that minimize the costs. It's written as sum of stored data, such that the convex combination of the data points give you the current state X. Simple convex problem, okay? And it is a control Lyapunov function. Why? Because if I jump from here to here, that's the stage, the decrease is exactly h. Remember, that was the property of control Lyapunov function. And if you jump from here to here, the decrease of the costs will be for sure less or equal than any convex function jumping from the same point to here. Okay? So what do you do the next step? Same thing. You repeat the iteration. Okay, you compute the actual measured cost, and you take the barycentric approximation of all data points. Very important point here. This is not highlighted in this slide. At every iteration, this function, the qx, these are the stored points, is a control Lyapunov function. Okay? Have questions? Good. So this is my LMPC. Do MPC. However, but with these two simple changes. Change the safe set, use the safe set at each iteration the way I explained it before. Add this cost to go as the barycentric approximation, so which means minimize over the lambda of the Q. Okay? If you read one of our papers on the transactions, there's going to be three main theorems, which is what your colleague was asking. One was, if you keep doing this, if you were safe before and there's no model mismatch, you'll be safe at the next time step. Constraint guarantees at iteration j, imply constraints guarantees at iteration j plus 1. It also, you can guarantee that the costs at the previous iteration is going to be less or equal than the, greater or equal than the costs at the next iteration. So you have performance improvement or equality. Okay? And also for linear constraint system, you can converge to the global optimal solution. I'm not going to do you the proof. I'm going to explain the proof. But the proofs are actually simple. They're all based on this property of control Lyapunov function. The trick is actually to compute the function. Once you have the function with that property, that's what the literature has shown in the past, that you have guarantees of safety and performance improvement. Okay? Okay, well, we came up with this idea, it was 5 years ago. Then I personally spent a couple of years trying to figure out why nobody's implemented this in this way. Is it really new and so on? So what's happening in reinforcement learning? So first of all, there's a lot of literature connecting optimal control reinforcement learning. Dimitri Bertseka's a new book that they sent me, very nice, connecting reinforcement learning and optimal control. It just came out a few weeks ago. There's a survey on Control System Magazine. There is my colleague Ben Reck, which is a nice blog on his talking about reinforcement learning and optimal control. But there are differences, okay? This is a continuous state formulation. I'm not discretizing the state. Constraint satisfaction is obtained in here, and usually constraint satisfaction is not really a focus on RL, at least not in a formal way it's done. The Q function I learned locally based on cost model exploration. I'll tell you more about this, okay? So if you just want to remember one picture, you have done your DP example, or somebody must be explaining your value iteration. And at some point, this will look like you have a grid like this, that changes with time, and the green, the more you iterate, the more green you get, where green means close to the optimal, okay? This, if you do ILMPC, is different. You're going to get a set of points, try, and they're orange because they're not optimal. At some point, you keep trying, you get more points, and then you get the optimal solution to go from here to here. And then you take the convex hull and the barycentric approximation, you have a local controller here. This is DP value iteration, this is ILMPC. It's a forward value iteration. DP, it's backward. Okay, what you lose by doing this, you lose that you have only local properties. Okay, here instead, you get a global solution. What you gain, you're not grading. Okay, and you can, you're not grading. Therefore, you can solve problems in high dimension. Okay. Think okay with this? What you'll see next, what's interesting is that in DP, one step backwards iteration makes total sense because it's global, okay? And so it makes no sense to do two-step. You could do two-step or two-step backward iteration, but there's no need of doing it. In ILMPC, because actually, in dynamic programming, you're exploring because you're global and you're going to every point. In LMPC, you explore because you're predicting. So if you do a forward iteration with one step, it's not going to work. You need longer prediction to explore, okay? And so that's also, actually, we have a nice theory that tells you how long you should predict so that you can start exploring. Your controllability matrix has to lose rank. If you are savvy about, if you know a lot about approximate dynamic programming, in this Bertsekas book, there is concept of aggregations, okay? People, if you have high dimensional state, then you don't want to do dynamic programming in high dimensional state. You do some aggregation. You have to figure out how to get this aggregation probability. That's very hard. But then if you have aggregation probability, you do this DP in a lower dimensional space, and then you go up by disaggregating in the original space, okay? So ILMPC is basically telling you, let MPC explore, and we'll basically generate aggregate state. This is a double integrated with noise. These are the aggregate states. Over 100 rollouts, if you take the convex hull of all the points, these are if you want, your state of the Markov decision process. State 1, state 2, everything inside the red, state 3, state 4, state 4. These are the aggregate state. And instead of using a linear, it costs to go a linear expression of your feature, I'm telling you, use barycentric approximation. As simple as this, okay? Good. And your barycentric approximation looks really cool. I think it looks better than the value function approximation, but that's just a taste. Let's go back to race. This is my race problem. If you want to learn these things, you have Chris Gerdes here is the world expert on racing. So his classes are just beautiful, and lectures as well. Here is written a minimum time problem to go from 0 till the end. You have some dynamics, you have some constraints. So how would you solve this if you take a Mackie class? How would you solve this problem? You write down the equation of motions. I spent a whole semester, half of the semester on this. These are just, body frame to global frame, but these are the Euler equations. And the hardest part in here are actually the forces to the vehicle, right? The forces to the vehicle are nonlinear function of size slip angle, slip ratio, friction coefficient, and normal load. And this, there are entire conferences on tires. You can go to conference on tires. They talk about this viscoelastic material. They tell you how to do this with finite element methods, how to put, how should you blend rubber with steel. And for control point of view, just do this, the nonlinear approximation. Okay, that's my tire. And the nonlinear approximation looks like it's higher if it's asphalt, it's very low if it's ice because you have less friction. Okay, it is a tough object. And by the way, if you're thinking, where is the input here? Well, the steering. By steering, you change the slip, the slip angle, right? This direction between the wheel this is the angle between the wheel direction and the vehicle direction. So that's your one input with steering. By throttling, you change the slip ratio. That's the wheel speed versus the vehicle speed. So, and then there's this other concept of race line. If you'd open a book on racing, they will teach you about the race line. It's these complex things to compute because in general, solve with dynamic programming. As you're approaching a curve, you have to open, you have to slow down, cut in, and then open again, right? This is called the apex usually. So the classical approach will tell you, run some experiments, get data, train, identify the coefficients of the function, okay? And now you have your tire model. You compute the race line, okay, with dynamic programming, and then you design a path follower to follow the race line. That's a very good design for doing racing. And actually, path following could be PID, but because the model is hard, you can do interesting things on path following to follow the race line. This is my controller. Okay, this is an ILMPC. This is the indicator function. It tells you it keeps summing until you you finish you get to the target. Okay, this is the how do you code minimum time. This is the Q function as I showed you before as you keep iterating. This is the safe set. As I showed you before, there is an SC because I'm using a convex safe set. So the convex also make computation intractable. And the only thing I didn't show you, how do you get A, B, C, D from the nonlinear dynamics? Well, it's a very simple idea. You take the kinematic equation, you know them well, so you do linearized, symbolic linearization, and then you take the dynamic equations, where this F appears, which you don't know well, and use a simple linear regressor. So it is a kernel function, okay, which tells you use data locally, only around you in space and time, and this is a linear multiplier of your features, which are states and inputs. As simple as this. Now you lost all the guarantees. The theorem doesn't work anymore. Because all the theorems I told you, performance improvement and so on, it's gone. Okay? Of course, you can do it robust, and there are papers that you can find from my lab about which guarantees can you give once you update these coefficients. But in general, it's hard. But it works extremely well. This is our 110. The code is online. This is at the end, once you have learned after 25 steps, it goes from 35 seconds to 5 seconds, okay? You can see the race line. Again, I'm not telling the race line, I'm not telling what are the tire coefficients, I'm not telling anything. Then we had Nitin. Nitin was a Stanford grad, came as a postdoc together, joint project together with Chris Gerdes, that we said, I want exactly the same code, exactly the same, even the random seed, okay, to work on the big car. Because otherwise, then, if you have to tune the big, the learning is fake, right? So if the exactly same code has to be pushed on our big car, and these are the experiments. Well, this just shows you it works with different tracks. The big car experiment looked like this. It's a pity you don't hear the audio. Is there a way to increase the audio here? It's pretty cool stuff. Okay, this is our test track. That was a loop. I was not happy about the cones. We go down to our California Proving Ground, and this is our nice test track here. I'm going to show you just experiments in this. There is a U curve, and then there's a chicane here, and same code again, different track. Lap 0. This is one of the examples where the initial feasible solution is easy. Just drive very slow center line. It's very boring. You know, this takes 10 minutes to go the whole lap, but you need to gather data, right? And then after, so you can see, that's only one piece, 100 seconds. At lap 16, you go down to 40 seconds, okay? So this is at lap 14. So you're opening, you see the chicane here, you go to the left, you slow down, and you cut through the apex. Constraint satisfaction right there. Good. We can spend hours looking at how cool these plots are, slowing down, opening and closing. If we are in a vehicle dynamics class, that's what we'll be doing. Every time I'm close to the end of the talk, but every time a student comes and say, it's very cool, I ask you, do you need all this to solve the problem? Do we need all this machinery to solve this problem? So do we need safe sets? So yes, you do, right? If you don't put the safe set at the end, okay, you're going to violate your constraints because you have nonlinear dynamics. We haven't tested this. There's no need to test it, and simulation shows you that you're going to just go out, okay? Although Nitin wanted to try that. I didn't. Do you need to predict to learn? This is exactly what I told you before. You do. If you have an MPC with horizon 1, you don't explore, you end up always going center lane, okay? You need to predict once you've learned. This is exactly this idea of storage. You don't. Once you have a lot of data, apply the input, which is a convex combination of it's a weighted sum of your stored input. This is the stored input at time I of iteration j, where these optimal coefficients are given by minimizing the barocentric function. As simple as this. This is super quick, 10x of a factor, and you're doing exactly the same thing. Of course, if you have disturbance, something changes, you need to go back and predict again. Okay? 5 minutes, 10 minutes to come to end. Okay? This was my, okay, what is new, what is old? A lot, for sure, vocabulary is totally new. I was writing papers written, simulation experiments, system ID. This was my vocabulary when I was writing papers as a graduate student. My students have to write papers where it's written episodes, training, learning, skill acquisition. Okay. It is the idea of using data to compute Lyapunov function safe set is new. Okay. I think if you just think about how we build this Lyapunov function based on rollouts, this is very different than solving the level set of Hamilton-Jacobi-Berman equation or finding the fixed point of a set value iteration. That is different, okay? Most importantly, I always try to ask this question, what does it do for the good of society? What is it, can we use this? And we can use some of this in what is new in this new architecture of remote embedded system, okay? When I was a student, this was not existing. You could not upload a controller in a car. Today, over-the-air updates will be standard in the next 3 years. Tesla is already over-the-air updates, right? Your autopilot is updated. And so these millions of cars that you'll have access to so that you can update the policy is actually quite impressive and interesting and different than when I was a student. And whether it's a good idea to do that and test it as people are driving, that's a different story. Okay, but I'm saying that is new. Okay, this is the system I work with in the energy field. This is a solar power plants. They're huge. They're 27 square kilometers, hundreds of football fields. Okay, have you ever seen one of these? If you see a video. This video this is a 754 megawatt. Okay, that's huge. All solar powered. You see these little rectangles? They are called solar trackers. They track the sun, and they are independently actuated. Okay, so they have a little battery here, takes back from the sun. There's a little motor, and they are independently actuated. You want to track the sun because then you get 30% more energy than a fixed tracker. Okay, and so if you think if a 100 megawatt plant has 2,500 rows, 25,000 rows. You do the math, you basically end up with 1 million PID per gigawatt that you can update because there are 10 PID on each system, on this system. It's a super simple system, it tracks the sun, okay? However, it's hard to make it robust because there are so many things that can, and I'd be happy to share with you. There are so many things that can go wrong even just doing this, okay? There's also another interesting thing that you do not want to track the sun when there are clouds. Okay, because there is more diffuse light than direct lights. So you want to go to an angle which is optimal depending on the cloud condition. Okay, so of course you pull this data up of all these trackers with their angle. Now we are installing also storage, and all this data are processed here, a few miles from here, by our software. Okay, so what are the real benefits of learning? This is always something that I ask. And when you hear about AI and learning out there in the world. Mostly, this is my definition, right? Skill acquisition, performance, and load reduction. But mostly, the word out there is about replacing the state with output. Step number 1. So don't do a state observer the classical way. Actually, just put a neural network so you can do output feedback from camera. That's quite interesting, okay? The second step is to say, well, replace the model and the agents of your environment. Again, don't do any model-based forecast. Just put another neural network, feedback based on vision. Okay, that's step number 2. You get rid of all the models, and you put another neural network here. Step number 3, replace everything, the state observer, the model, with a big neural network. This is what is called end-to-end control, okay? And I claim that this is a very bad idea, okay? And it's not that I claim, we shouldn't be teaching, we shouldn't be entertaining this idea. It is just not a good thing to do. And I'll be happy to, sometimes I give this talk at different audience. Maybe I'm preaching to the choir here. But sometimes people look at me weird. Why are you saying this? We can, I work with companies. I work out there. It is hard to use composition to calibrate, to test, to explain to a lawyer. And we shouldn't be doing this. However, and by the way, I'm taking this class on I'm sitting in this class of my friend Ben Recht on machine learning. And I'm learning, many of the things I know, but learning interesting new things. But some stuff I forgot. I forgot about the perceptron. How many, you guys, any computer science here? You remember the perceptron story? This was a New York Times telling you that the Navy revealed the embryo of an electronic computer that expected to be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This is New York Times in 1958. Okay, and this is a stochastic graded descent with a hinge loss. That was the perceptron. It's here. It's a stochastic graded descent. It's the simplest form of graded descent. So I'm saying maybe the whole field started with a big hype. Okay, and so now we just cannot stop it. But anyway, I promise I'll be positive, right? So machine learning is good at this, right? Classifying. And very good for my searches. So if you go back to the solar tracker, what angle you should be in, it depends on the clouds. And it's very hard, actually, to make a cloud. Imagine doing cloud modeling in the sky, right? How they propagate. And in real time, this is super complicated. So what you can do is actually put a neural network on an image that looks at the sky and train a diffuse light versus direct light estimator to close the loop on these trackers, okay? So this is a product. It's called True Capture. We have to use machine learning. Okay, so this is a product. This exists. These are all our solar power plants around the world, 20 gigabytes. It's 40% of the market. This system delivers 6% efficiency gain. That on a 20 gigawatt fleet, this is 1.6 gigawatt. And this is 3 coal power plants, okay? So these are real benefits, okay? This has been obtained by using data-driven exploration, okay? And so this is done here, a few miles from Stanford at Nextracker. This is the next thing I want to change. When you buy a car, Marco thinks you're not going to buy cars anymore. So I'm much old, not much, but I'm older than Marco. So in my lifetime, I think I'll still buy a car. And there's this ugly number, 25 miles per gallon. What the heck it means? So this is obsolete. And even if Uber is buying cars, they have to look at the efficiency of their fleet, right? And so do you know how this number is computed? There is a test which is the same for all the United States, and there's a profile, which is total nonsense, right? This is our fleet of 5 hybrid vehicles, a very complicated powertrain driving around the Bay Area. It's a big project with Hyundai. And we're basically recording data as we go back and forth from Fremont to Berkeley and other areas. And you can basically learn traffic patterns and deliver a powertrain control design for that road, okay? And so this can be done. There's technology for doing this. And this is what is in production. In production, there is something called charge deplete, charge sustain. Use the battery first and then use the internal combustion engine. For that road, for that traffic in the morning, it's not the best thing to do. You should use a blend of battery and internal combustion engine. Okay, I'm done. I think hopefully I'm not over. I told you about the role of constraints and prediction. I told you about interesting problems, what learning can bring. And actually, I've been working a lot on trying to think about how to introduce all this in our curriculum early. This is our experiment, undergrad experiments for teaching this robot how to do the ball in the cup. Charlotte is not happy about it. So, we all agree this is learning not in the Gestalt sense, right? We are coding these algorithms, okay? So there's no learning here. But students get excited when they see this thing working, okay? This is Tony. I guess he didn't believe in the theory. Okay, there's a lot of more videos on the web. Thank you. Questions?
Okay, so in the case where you eventually you reduce the computational load on the computer because you've learned the track and you learn the environment, I guess at what point would you switch back to like adding the prediction back in with like
Yeah, very good question. It's actually from the system, from the setup we have, it's very natural. As long as it's fewer outside, if that problem becomes infeasible, okay, the little LP problem, which means you are outside the convex hull of any data point you have, then you're infeasible. You need to predict again. You don't have data that tell that you can interpolate. Okay, so the way we do it is actually as soon as that LP becomes infeasible, then you switch to an online line optimization with prediction. And by the way, that one doesn't need to be solved with an LP. That could be a neural network that interpolates the data. Okay, but we like LPs. Yeah. Make sense?
So
Here.
like, in the case of like the
So it's as simple as, remember what the policy is here. Okay, so this is your policy. Is the lambda come from solving this optimization problem. This optimization problem is constraints that for a given state, it might be infeasible. If this is infeasible, it means that you don't have enough state that you can interpolate to find the lambdas that solve this constraint, okay? And so that's the time to make predictions again. Yeah, yes.
I guess kind of going off with him. So like say like someone spilled a glass of water on the track and that changes the tire coefficient. I guess would that come into play with the lambdas? Or?
Correct. So what will happen is that this will become infeasible. You will go back and do predictions, and now your kernel will use the data, the latest data. The kernel is it's local data in space and time. So it's a forgetting factor with all data, and that will learn your patch at that point. No guarantees, right? You can make it easy, and of course there is no feasible control at that. Yeah.
And so here, for example, for the track, let's say there's like just a temporary disturbance. I can the system, for example, predict for the time there's disturbance, and then remember the old track when it can just begin again, or does, if the conditions are normal again, does he have to relearn the standard trajectory again? Or he can remember the first that he learned?
So again, let's see. Let's use the word learn. Let's see what we store and what we in this system here. Okay. If you go back to this guy here, okay. These are the safe side and cost to go are task and track dependent. You change your constraints, you change your objective. These two things will change. So you have to recompute these two things. Even if if you talk about, so these are a lot of things. If you have a disturbance and the task is always the same, this enters in here, okay? And so yes, this will be, if the kernel is a forgetting factor, you won't be able to predict that this is gonna be, it was there 5 minutes ago. Also, what is the best thing to do there is you have to first formalize what's the best thing to do in that case. Yeah. Yeah.
Is there any way to, it seems pretty data efficient, like only 10 or so iterations on a lap before you can start getting good performance. But is there any way to like generalize it in some way? Like if you're trying to fly through a forest, not all forests are the same, but they're sort of similar in some sense. So I'm just wondering if there's a way to like do some sort of generalization without having to relearn this.
It's a very good question. I guess that's the holy grail of these people. I don't have a good sense of it. We are thinking about it. It's always a problem of, if you're interested in writing theorems or even in something that works very well in practice, and sometimes the two are hard to combine. However, what I can say, I mean, your point is very important. This is the critical part of this. Imagine trying, where is this guy here? Where's the lab? I don't know, here. But imagine trying to basically, now you're doing MPC, right? And you have this prediction stochastic. Imagine trying to update with value iteration the policy around here. That won't be data efficiency in real time at 20 milliseconds, right? So yeah, I think this, if you take what has been done in the past, you bring in this context, and maybe use some statistical learning theory, you can probably generalize these things. So some of my students are working in this area. Yeah, very good question. Yeah.
So it seems like in these examples you know the dynamics pretty well, but say you wanted to land a quadcopter optimally or something and need to reason about ground effects where you have a really bad model and like don't even have a good way of parameterizing it sometimes. How do you think you might apply this?
Yeah, I don't know. This is more like the God model. What if I knew? It is, actually I have different questions there. I don't even know what it means it works. Does it work means to generate a video for ICRA? It is a big problem, right? It doesn't mean that after 100 iterations, so of course you can do some statistics, okay? I try hundreds, okay? I want to have a model that learns, okay? And over the past 1,000 iterations, okay, my percentage of failure decreases. So I look at the window, so this could be a good definition it works, okay? So in that case, no, you would need, in that case you need to pick a model, okay? And what I'm claiming here, I actually, this stars, you say I know very well the model, but not really. I've used a linear kernel here, right? You could use a piecewise linear kernel or a neural network, the ReLU, and it would, I don't have proofs, and you wouldn't have proofs with neural network either, so I think it's fine. I don't know if a linear kernel, for your application, if just a simple linear kernel would work, or you need a deep neural network with a ReLU activation function. Clearly, these neural networks are very good at classifying, right? So I haven't seen a very convincing story that's a very good approximated dynamical models, with the exception of, okay, of course, there are piecewise linear functions. Piecewise linear is better than linear, right, in general.